You all see the right screen, right?
Yes, we see the correct screen.
Perfect.
All righty, take it away.
Okay, thanks, Elias. So yeah, thank you for giving me that opportunity to try to introduce some of the work our group have been done, and also some more broad aspect of the NMR of batteries. So first, I would like to state that feel free to interrupt if you have any question, if something isn't clear. Yeah, just do it. Okay. So with that, let's start from the ground up. So NMR is a physical phenomenon that occurs when a nuclei that possess a magnetic moment is subject to a strong external magnetic field. So when a nuclei possess a magnetic moment, it means that the nuclei behave like a tiny dipole magnet. You might have seen already that type of representation. So when such magnet is placed in a strong magnetic field, it will seek to align with the strong external magnetic field that you just put in. And by doing that, it will follow a precession movement, which will have a distinct frequency, which is also referred as being the resonant frequency or the Larmor frequency. This physical phenomenon is also found for other particles like electron, and it's actually what is used in electron magnetic resonance that Howie presented in a previous talk. So the nuclear magnetic resonance is only just the physical phenomenon that is used by NMR spectroscopy to prove the local environment of a nuclei. So here I'm showing a proton NMR spectrum of a molecule that contains a methyl group, CH3, an hydroxyl group, OH, and a CH2 group. These three signals are here because we just recorded the spectrum of ethanol, which any good organic chemist might have seen at some point. Another well technique that use NMR is actually magnetic resonance imaging, or MRI. And in an MRI, what is going to happen is that the NMR signal are going to be recorded at different locations and used to recreate an image, like shown here with the brain picture. Another technique that has been, so the other technique that I mentioned, EPR, that was presented by Howie in a previous talk, is in fact very similar to NMR, at least in the principle. In EPR, we don't really observe the magnetic moment of a nuclei, like the name implies, but we observe the magnetic moment of an unpaired electron. So here I'm showing you again that spectrum from ethanol. And here and here, I put it two EPR spectrum. So the first one is for manganese 2+ ion that are dissolved in a mixture of EC, DNC. So people from batteries are gonna probably recognize this. And on the right, you have an EPR spectra of an organic radical. So the main advantages of NMR is that it has a much higher resolution, which means that roughly the distance between two signals is much higher in NMR than in EPR. But on the other side, the EPR technique is much more sensitive than NMR, and you will see later why NMR sensitivity is not great, to say the least. So it is also worth mentioning that EPR and NMR are both pretty complementary, as NMR is usually used on diamagnetic system, while EPR is only going to work on paramagnetic system because you need to have unpaired electron, but otherwise it's not going to work. So now to give you a brief introduction on the application of NMR spectroscopy, and that's pretty much to show exactly what Elias meant by NMR is a broad technique. So NMR is often used in a wide variety of application, and one of the most used application for NMR is probably chemical analysis, where molecules and their motion can be identified either in the liquid or in the solid phase. In fact, you can also do NMR of gases, but it's usually not the first way to do it. So in biology, NMR spectroscopy is particularly useful as it allows you to study protein, while there can be directly in a cell, which is called in-cell spectroscopy in that case, and this is pretty powerful because that avoids the user to skip ahead the extraction of the protein, the crystallization, if you want to do that you would have to do for XRD or so on. So it's a pretty straightforward technique and a pretty nice one. But NMR is not limited to small molecules, as you probably know from the title of my presentation. NMR can also be quite useful when you are looking at material science. And in fact, with NMR and material science, you can probe the structure of the materials at the atomic level. By doing that, you have a powerful technique for materials that lack long-range order, like heterogeneous catalysis, glasses, polymer. For these three materials, the diffraction techniques that is usually used for material science is not that informative, but NMR, on the other hand, can give you a lot of information. That material science also, of course, rely to batteries. That is the reason why I'm making that talk. So we're going to come to that point a bit later on. So another well-known application of NMR is clearly the imaging techniques, which is probably also the most well-known and famous reason why NMR indirectly is well-known from the public. So in this type of application, what you're looking at is the spatial distribution of proton, which is obtained from an NMR signal and used to reproduce an image. So this type of image provides a much better contrast for soft tissue of the body than X-ray does. So both X-rays and MRI image are pretty complementary for that matter. Also, on a side note, I should mention that while MRI is usually looking at proton signal, you don't really need to use proton to get an image. You could theoretically, and we'll see later that it's in fact done, you can use other nuclei. So on top of these three main applications, NMR can also be used in many other fields like chemical engineering, geology, and especially for oil exploration in industrial processes. And in that case, quality control has a big part of it. And also, I mean, I find it interesting to mention that it has also some exotic application, like in World Heritage, when they want to restore painting or so, they are sometimes using NMR because it's a non-destructive techniques, and that is always a good point for when you want to look at heritage. Yeah. So now I'm going to try to make it simple and concise with the fundamental of the NMR theory. But yeah, if something isn't clear, feel free to stop me. So, like I said, we're going to have to talk about the basic, and this starts with the concept of nuclear spin. So it's a fairly difficult concept, but it's fundamental at it is actually what we observe in NMR. So to start with, you have to picture the nuclei at the center of the electron cloud of an atom, and these nuclei behave like a tiny magnet. So like any magnets, the nuclei creates a magnetic field, and these properties can be seen as a result of the movement of the nuclei containing positively charged proton. So this is a simple image, but this allows us to understand why the magnetic moment of a nuclei is related to the nuclear spin. Yeah, but now you might be still wondering, what is a nuclear spin? And here it goes. So bear with me, that's going to be a complicated one. So a nuclear spin is a quantum angular momentum, but I'm pretty sure you have no idea what I meant by that. So let's try to decompose that sentence. First, the angular momentum is normally used in physics to describe a rotation movement, like you would find with a spinning top. And that angular momentum can be used to predict the movement. Also, in classic mechanics, this type of angular momentum can vary continuously. But you all know that nuclei doesn't follow this type of classic mechanic behavior, but due to their small size, they follow quantum mechanics. And in that case, the angular momentum can only take discrete values like 0, 1/2, 1, 3/2, and so on. And this would actually mean that the nuclei can only spin at a certain speed. But the spin is a bit more complex, as it is not just a quantum angular momentum, it's an intrinsic one. And what that means is that even if in quantum mechanics, the angular momentum of a particle will depend on its history, this one way of describing that or picturing it is like if you are eating some water molecules, the motion and the angular momentum of the molecules can increase and reach higher values of the quantum number J. But for a particle or a spin, this will actually not happen. In fact, a nuclear spin of a particle is completely independent on its history. This means that the nuclear spin of proton, which is 1/2, will always be and stay 1/2. And that's why the nuclear spin is an intrinsic property of the nuclei. So after that, I hope you are still awake. And I know it's early, so you might be still wondering, what is a spin? And the short answer is that first, the nuclear spin is not related to a rotational motion, but it's a property like mass or charge. So I know that concept is a bit weird, let's just say it. And it's difficult to grasp just because we don't have a macroscopic object that can represent or that can help us observe what a spin is, which is not the case, like, for example, the mass or the charge concept of a particle. But what I need you to understand is that in the end, the spin is just a tool. And that is super useful as it best describes the physics and the properties of the particles that we can see, especially in NMR. So yeah, do you have any question or should I continue?
I have maybe one quick question that you can explain here. Why do different nuclei have different spins?
I'm just gonna explain that like literally in the next slide.
Beautiful.
But yeah, you're gonna have the explanation. It's gonna be a quick one, but yeah. If that's it, I guess I should just go ahead. So why is it not changing? Okay. So literally, to answer that question, the reason why different nuclei have different nuclear spin is that to obtain the actual nuclear spin, you have to follow a few simple rules that are being described in that table to obtain that value. So what you really need to understand is that, for example, if you take the carbon-12, you're going to have a spin values of 0, while if you take the carbon-13, you're going to have a spin value of 1/2. Yeah, if you want to play with this rules, I'm not going to really extend anything here, but the nuclear spin, you might know that, but yeah, now that it's just a combination of the proton and neutron, which themselves have a value of spin, and when you add them up to form the structure of the nuclei, you end up with either all of them canceling out, or that's gonna not be the case. They're gonna add up and make that. So yeah, I hope that answers your question too. So one thing to know is that NMR is only looking at nuclei that have a magnetic moment, which means by definition that it's only look at nuclei that have a non-zero nuclear spin. So for example, in that table, all of these nuclei that would fit that combination of mass and atomic number would be NMR inactive. But on the other hand, all of these are NMR active. So one thing that I've been extensively talking about right up until now is the spin. But now, if I give you that equation, you can understand how the spin relates to another very important property of the nuclei, which is called the gyromagnetic ratio, or gamma. And it's a value or a parameter that it's usually expressed in radian per second per Tesla. And we're gonna come back to it a bit later. But what you have to know is that when the gamma value increases, the magnetic moment will increase because of that equation. And if the magnetic moment of a nuclei increase, that means the NMR signal of that nuclei is going to increase. For example, here I'm give you a comparison, and you have, or you might already know it, but proton is one of the most NMR sensitive nuclei that we have. But in contrast, the carbon is only a fourth of the gamma, so the gyromagnetic ratio, sorry, of carbon is only a fourth of the one that proton. So by that definition, carbon is going to be less sensitive too. So apart from the gyromagnetic ratio, you have another very important property of an isotope, and it's that the natural abundance of it. So this is just a representation of the mole fraction of an element that is naturally occurring. And for example, again, if you take the proton, it's almost 100% abundant. But on the other side, if you take carbon 13, that is the NMR active isotope of carbon, it's only 1.1% abundant. And from that sentence, you can pretty much figure out that if your natural abundance increase, your NMR signal are going to increase, because you're going to have, in fact, more spin working to give you signal. So one thing I should mention is that natural abundance is not the end of the line when you have a complicated isotope you want to work with. And in fact, you can always try to enrich a sample, but this is often expensive and can be time consuming. So yeah, that's why you have to pick your nuclei carefully. So from these parameters that I've described and are quite useful from an NMR spectroscopist point of view, these type of values are usually available in large table like this one. So this is just a fraction of what is actually available, of course. But yeah, this is really useful. And anyone that I've done NMR spectroscopy, I'm pretty sure at one point looked at one of these tables, because it's the first step you would take to evaluate how difficult a given nuclei might be to study, which is important when you want to start a new project, for example. So here I'm taking a few examples. So the first one is, again, proton. And from now on, I'm pretty sure you have a very good idea that NMR of proton is popular because it's pretty much the most favored nuclei. It's a spin half, almost 100% abundant, and one of the highest gyromagnetic ratio you can get. On the other hand, if I go back again to carbon 13, still spin half, but here the natural abundance is only 1.1%, and the gyromagnetic is not that bad. So the frequency, like I said, is only like a fourth of the proton. But if you really go in the more challenging nuclei, you would find in that case nitrogen 15 and oxygen 17. And here you're gonna have some serious issue because, well, first, both of them have a very low natural abundance. And also, if you look at the gyromagnetic ratio, they are pretty low. So when you're dealing with at least these two nuclei here, that's really the natural abundance that is the problem. So you're gonna have to rely on isotopic enrichment. So now I just want to take a quick break from the theory just to make sure you are still awake. And I'm going to talk about some practical aspects of NMR. So imagine that you want to get an NMR spectra. So of course, the first thing you need is going to be a sample, right? So the sample can be either liquid or solid, depending on the type of sample and the type of system or even experiment that you want to run. And you will have to choose from a variety of sample holder. So usually for liquid sample, we just use a simple NMR glass tube that is looking like that. And here in particular, that's a 5 mm model, which means that the diameter of the tube is going to be 5 mm. But other sizes are also available, and you have to just use the one that is most suited for your either your experiment or the amount of sample that you have. On the solid side of NMR, the choice of sample holder is a bit less straightforward, as you're going to need to work with powder, which are going to have to be packed in a NMR rotors, which are pictured here. So I'm sorry, I don't have a quarter or anything. That picture doesn't belong to me. So you're going to have to deal with the scent from our Canadian friends. But I'm hoping that you get the idea that these things are tiny. And I'm not going to go into too much detail which one you would choose for different type of application. But from what matters to you and probably to me also, is that for battery materials, the best size rotor that you're going to have to work with is usually the 1.3 mm rotors, which are the tiniest on that comparison. And the message that I want to give you is that working with this type of rotors is not always that easy, and especially when you have to work in the glove box. But with practice, like everything, you can do it. So now that you have your NMR sample ready and packed or put in a tube, what do you do? So to do NMR spectroscopy, I know it might sound silly, but you need an NMR spectrometer, right? And in fact, an NMR spectrometer is not just one single unit. It's composed of 3 main parts. I'm putting the benchtop NMR on the side here, not because I don't like it, just because you can't do solid-state NMR on a benchtop system. So like I say, 3 parts. First, you have a mag.
Sorry, there's a question on the last slide that just came up. Why does the size of the rotor matter?
Okay, so I'm just going a bit ahead of the rest of the talk, but the size of the rotor is going to dictate 2 things. First, it's going to dictate the amount of sample you can put at one time in your spectrometer. So in general, the more sample, so I mean, the more powder you have, the more spin you're going to be able to work with. And so the higher the signal intensity will be. So for example, when you're dealing with a very low sensitive nuclei that has a very poor, or not poor, low natural abundance, you can kind of compensate if you put a lot of powder. So for that, a large diameter would be nice. The second part, and I'm going to explain more on that later, but is that in solid, if you look at actually the rotor, you see that these are caps. So you put the powder from this side. These are meant to be spun because in solid-state NMR, you spin the rotor at a certain frequency or speed. And depending on the type of experiment you want to perform and the type of system that you have, you might have to spin faster or you could spin slower. The thing is that the bigger the rotor, the more powder you can get, but the slower your rotor will be able to spin. So to give you a quick value so that you have in mind, 7 mm or just these ones are not that common or usually used, but the 4 mm is very common. The maximum speed at which you can spin, or the frequency in that case, would be around 12 kilohertz. So it's in kilohertz, not turn per minute. So it's already quite fast, but still not that fast when you compare to a 1.3 mm rotors that can reach 60 kilohertz. So yeah, that's what I meant by depending on the system and type of application. I hope that answered the question. And sorry if I'm skipping steps. I don't want to be too confusing because there is a lot of factor to take into account. You are dealing with NMR, especially in the solid. So yeah, hope that's clear now. So going back to the actual NMR spectrometer. So like I said, the first part you're gonna have is usually what people see the first when they enter the room is the magnet. And in fact, it's usually a superconducting magnet because you need to be able to produce a strong and an homogeneous magnetic field. To give you a bit of some values here, most magnetic field range from 2.3 Tesla up to 23 Tesla, so 1 order of magnitude higher. So in fact, here I've put it a picture that is coming from the strongest magnetic field available at UCSB, which is here 18.8 Tesla magnet. So one note on the superconductivity of this magnet is that it's the magnet, in fact, is a coil that is a superconducting one made of a special alloy that is going to be then cooled with liquid helium and protect with liquid nitrogen to be superconducting. And this is how you create very strong magnetic field, not neodymium magnet or permanent magnet. But like you would have with the permanent magnet, this is not also an electromagnet. The magnetic field will always be on, and that's usually put on this on the door, because when you are entering an NMR facility, you have to remember that all of these things are pretty much large magnet with no off button. So when you are going close to them, you have to be careful and not, for example, carry metallic keys, or you're gonna have a bad time. So yeah, if at some point you go into an NMR facility, just be careful and follow safety rules, please. So the second part of the spectrometer that is a bit or often ignored unless you are an expert and you care about that. But that's the NMR console. So on the picture, it's over there in the background, but I've enlarged another picture. So this is coming from Bruker. This is also a Bruker. So I feel like it's relevant in that case. But I'm not going to take too much time describing what this is. But what you need to know is that it's usually a large box that is filled with electronic stuff. And that is that box is responsible for the excitation signal, so to create that signal, and also to record the NMR signal. And the last part of that detection chain is the actual NMR probe. And so I've put a picture here. So nothing is to scale, by the way, because this part is just going to go in the middle of the magnet. And this is actually where your cell phone is going to be. And the probe here is responsible for both the excitation of the signal, the sample, and the detection of the signal. So now that I've put a bit of practical aspect, I'm going back to the theory. And now I just want to explain why you, from the beginning, need to put your sample in a powerful magnet. So up until now, we've only talked about isolated spin, right? Since I was explaining the concept. But your spin, if your spin is possesses a non-zero magnetic moment, which is denoted mu, that means that it's an NMR active spin, and you can do NMR on your sample. But a sample, in fact, is not just one spin, and it's usually a much better description to consider a spin population. And the thing is that these spins, they can have different direction, and in general, you have a random distribution of these spins, and so you won't have a microscopic magnetic moment. So something is problematic if you want to do NMR with that, right? Because you are missing the main part that we want to. But to get that moment back, what you need is that you place your sample now in a strong magnetic field. And like I discussed earlier, the magnetic moment, individual magnetic moment that act like tiny magnet, they are going to start to align with the B0 field, so the external field. And it's pretty much exactly what would happen if you put a compass in the Earth magnetic field. The compass will try to always stay aligned with the north magnetic pole, and that's why we use compass, even if now GPS is more trendy, but yeah, sorry, GPS doesn't work here. So this phenomenon for nuclei is called, in fact, the Zeeman interaction. And you might have heard that word because it's not only for NMR, it's much broader than that. And it was, in fact, introduced for optical spectroscopy technique. But now, since you know that the nuclei are quantum particles, their stationary states will also correspond to discrete energy levels. And one thing that I haven't mentioned, but I'm going to correct myself here, is that this alignment of the spin with the external field are going to follow a precession movement. And so something like this. Now, and that precession is going to have an angular frequency, which is given here. And you see that omega 0 frequency that describe the angular frequency of the precession movement is directly related to the gyromagnetic ratio and the strength of the magnetic field. So I will also mention that in particular that angular frequency is also called the Larmor frequency, and you might have heard of that already if you've done some NMR, and I'm going to go back to that concept a bit later. But yeah, remember that one, it's an important one. So now that you are applying B0, so you have precession and the Zeeman interaction is working. But like I said, if you just go back to the isolated spin, you have a magnetic moment. And if you do a quantum mechanics treatment of that particles, you're going to realize that, like I said, the different energy level are quantized. And in fact, you have MI level, where MI is going to be a function of the actual spin value of the nuclear spin. So these sublevels are going to be degenerated or mingled. And when you then apply the magnetic field, the Zeeman interaction kicks in. And now you are actually splitting the sublevel into different values that are non-generated levels. So if you take a spin half, like proton pictured here, you're going to have two stationary level, because I is 1/2, so 2 times 1/2 plus 1 equal 2. And these two states are denoted alpha and beta. In the alpha state, Mi is the plus 1/2 position, and in beta, Mi is equal to minus 1/2. And when you are in the alpha state, the spin are aligned with the magnetic field, and that's called the spin up state. And in the beta state, that's the reverse. You are anti-parallel, and now your spins point down, and that's why we call them spin down. You might know that already, but yeah, these type of arrangement are not fully random, or they are fully random, but the energy of each state are slightly different. And in fact, the alpha state is preferred. And if you consider now the energy difference of the alpha and beta states, I'm picturing it here as denoted delta E, and delta E again is going to be proportional to the gyromagnetic ratio and the strength of the magnetic field, and also the h bar constant. So still, if we are in isolated spin like proton, like I told you, you can be either in the alpha state or beta state. And I told you that there was some slight difference between the two energy levels, the actual value. So now, if you consider no longer an isolated spin, but a spin population, that means that you're going to have some statistics playing with you, and you're going to have a slight difference of population, because that alpha state is slightly favored than the beta states. That difference in population in the states is actually quite important. And the reason is that this is what NMR is playing with. And to give you a reference point of view, if you are working at 11.8 Tesla, which is already quite high magnetic field, and remember that the magnetic field make that difference of energy even higher. If you consider now 100,000 proton nuclei, so or spin, if you want, the population difference between these two states will only be 5 more proton in the alpha state. So yeah, 100,000 proton nuclei, only 5 that are going to be in a different state. So this is pretty much the reason why the NMR sensitivity is so low, because that difference in population is very tiny. So like I said, like I said, the sensitivity is low, but yeah, the principle of any spectroscopy technique is that now you're going to have the opportunity to move the spin from the alpha state to the beta state with an incident photon, and that photon needs to be at the right energy values so that the transfer is going to be done, and to actually the energy of that proton needs to match the resonant condition, and that's why NMR is a resonance in the name. So yeah, just to give you again a bit of values and context, that energy frequency is going to be a function of the Larmor frequency that I talked about earlier, and that's why I told you that the Larmor frequency was important. And from that table here, you can see that if you have, for example, 9.4 Tesla magnetic field, the proton is going to resonate at 400 megahertz, while the lithium is going to be around 155.5 megahertz. But if you double now the magnetic field, you are also doubling the Larmor frequency of every nuclei you are working with. So yeah, that's something that is important to have in mind. Also, I should mention that is the NMR energy level that are usually used are in the range of the radio wave frequency. So radio wave frequency is quite a low energy level when you compare to, for example, gamma rays or X-rays. And for that reason, because of that low energy level, this is why NMR is a non-destructive technique. You are not going to create radicals or excite anything. You're just flipping a spin, and that's pretty much it. Nothing else is going to happen in the sample. So with that, I think I should ask you, do you have any question? No?
I want to ask if you could provide a sort of quick summary again on the side of why the spin population is really the signal that we deal with here.
Okay. Yeah. Just to make it simple, whenever you have a splitting of energy level, and that's not just for NMR, that's any spectroscopy technique, you are always dealing with different energy states, either because they are from the coming from the nuclear spin states, or even when you have an excited molecule, or you've got the ground state and you can excite different transition. That's what you would have, for example, with infrared spectroscopy. So when you are doing spectroscopy, you are playing with this energy level, no matter what they are. And when you are doing NMR, the energy level that you are using are the one produced by the splitting of the nuclear spin states, so the alpha and beta. And because that splitting is very weak, you don't have much population difference. You can't really, all of the, if you consider that picture, all of these spin are canceling each other's. So you can't ask that spin to go up because that state is already filled. But these few spin that are like occupying the alpha state, they could be put in the beta state. And by doing that, you are actually playing with an energy transition, which is what any spectroscopy technique would do. If you take, for example, infrared spectroscopy, this type of population difference is much higher. You have very few molecules that are excited to higher energy level, and that's why infrared spectroscopy is quite sensitive, because you have lots of spin that are in the ground state of the molecule, and you can just put some infrared light on your sample and just excite this transition and go to a higher state, and then look at your actual infrared signal. For NMR, it's going to be the same, not in the same radio frequency wave range, but it's going to be the same. The problem being that most of the beta state is already filled up, because the splitting, the Zeeman splitting, is not that favorable to the alpha state. And that distribution comes from the Boltzmann distribution. I haven't talked about that here, but yeah, that's why that's been, population is very small. I hope I answer your question.
Yep.
Okay.
Thank you.
Yeah. I know that I'm bothering you a bit with the theory right now, but bear with me, we're almost at the end. But yeah, what you here need to remember is the fact that NMR sensitivity is low, which is really the bottleneck, or the one of the main issue that NMR spectroscopy has to deal with, the low sensitivity of the technique. Because if you consider any other spectroscopy technique, or almost any other, the sensitivity is super high. If you take infrared, that's, for example, really high sensitivity, Raman 2, even if you have like saturation phenomenon. But yeah, on the other side, NMR is really like the black duck here, that yeah, sensitivity in NMR sucks. That's the only thing I can say. And the other concept is really the resonance condition, that if you want that transition to occur, you need to be at the right frequency. But yeah, so with that said, I'm going to move on. Yeah, yeah, one thing I can mention, you know that NMR deal with different nuclei, and the reason that you have to match that resonance condition, and the fact that the nuclei have very different frequency. In NMR, when you're working with proton, you're not going to be bothered by any other signal than signal coming from actual proton. You don't have like overlap because the signal are very well separated. So I guess you could say in that case that resolution is really a big plus for NMR. But yeah, just wanted to put that on the side. So now I'm going to give you a brief overview of the main interaction that you found in NMR, because all of these things are very important. So if you look at the slide later, I have put much more details in that, but just to save some time and also some headaches, I'm just going to give you the short version here. So up until now, I've been extensively talking about the Zeeman interaction. I'm pretty sure everyone is going to agree with that. But the reason is that this is the main interaction that is responsible for your actual NMR signal. But you still have other interactions that are going to affect your NMR signal, and they are still important to understand. So the first two interactions that you will encounter when you are doing NMR are the chemical shift and the J coupling. So here, you might have heard of them, or you might already know them without realizing if you ever recorded a liquid state NMR spectrum. For example, if you're an organic chemist, you are dealing with that on a daily basis. So first, the chemical shift is responsible for the position of an NMR signal in a spectrum. And this interaction is the one that allows you to distinguish different local environment in your system. The J coupling, on the other hand, is the interaction that is responsible for the multiplicity of a signal. So that's why organic chemists deal with doublet, triplet, quadruplet, and so on and so on. And this is most of the time relevant for liquid state NMR, just because of the example I gave you. But it also exists in solid state NMR, but it's much less relevant for just to make it short. So speaking of solid state system, in that case, well, you have a couple more interaction that shows up. And first, the chemical shift gets a bit more complicated, as you are now also dealing with the anisotropic part of the interaction, which is called chemical shift anisotropy. Yeah, not very original, but I'm going to call it CSF from now on. And on top of that chemical shift anisotropy and chemical shift, you're going to add two more interactions. So first, the dipolar coupling, which is fairly straightforward to understand. It's just the same type of magnetic interaction that you would have between two tiny magnets, because like I told you, spin are behaving magnet. So this is a through space magnetic interaction that are going to be dependent on the gyromagnetic ratio of the nuclei involved in the interaction. And it's going to be also inversely proportional to the cube of the distance between these two nuclei. So after all of this, if you're also dealing with quadrupolar nuclei, so that means you have a spin number that is higher than 1/2. And to give you a bit of context, almost 70%, 74% of any NMR active isotopes are quadrupolar. So maybe not the most well-known interaction, but definitely an important one, and especially in solid. In liquid, that doesn't exist. So you're lucky on that one. But just to make it short, this is a much more complicated interaction to describe and to work with in general. But the bottom line is that when you have quadrupolar interaction, the spectra are going to get much more complicated, because that interaction is going to affect the line shape of the signal, and it will make them broader. One thing is that usually when you're working with quadrupolar nuclei, you want to work at higher magnetic field, as this can like limit the damage the quadrupolar interaction can do to your spectra. And finally, and usually people don't care too much about that one, but if you are working with battery materials, there is a fair chance that at some point you're going to interact with another type of interaction, which is called the paramagnetic interaction. So here again, it's a bit more complicated, but I'm going to try to make it very short and simple. And to do that, what I would like you to keep in mind is that the paramagnetic interaction is in fact multiple sub interaction, but it's going to make two things. First, your signal are going to be significantly broader, even if you have a spin half nuclei. And then the shift, so the chemical, in chemical shift, are going to be much larger than what you would expect in a purely diamagnetic sample. So from now, with all of this knowledge in your mind, you can pretty much understand that first, I haven't told you that, but every interaction have different amplitude, and that's what the circle are picturing. The bigger the circle, the larger the amplitude. Of course, you want to have the Zeeman interaction as big as possible, because all of these interactions are usually treated as a perturbation of the Zeeman effect. If one of these interactions becomes much bigger than the Zeeman interaction, you are basically no longer dealing with NMR signal. So you have to change your theory to fit your system. But also what I'm pretty sure you understand is that when you work with NMR, well, depending on the system that you are playing with, things can get complicated very quickly because of all of the potential interaction that are at play. So I hope that was clear. And now I'm going to move on with to one thing in particular, just to save time, but I need to mention something. And that's this one, the magic angle spinning technique. So this technique is particularly important when you are dealing with solid. And in fact, that's almost nowadays the most basic form of solid state NMR. And if you ever looked at a paper when they were doing solid state NMR, there is a 99.9% chance that they were doing magic angle spinning. And that's why I want you to have some knowledge about it. So the principle is fairly straightforward, and that's pictured here. When you're putting your sample in the magnetic field, it's not going to be aligned with the magnetic field, like the actual sample. It's going to be put it at a very specific angle of 57.7 degree, and in fact, it's even more precise than that. But yeah, I'm making it simple, or at least I'm trying. And then you're going to start to spin that sample at very high frequency. And this is what I was talking about a bit earlier. That frequency can range from just a few kilohertz especially if your rotor is big, like the 7mm rotors, you won't be much going much faster than 5 to 7 kilohertz. But you can also reach the much higher spinning speed, and you can in fact reach about 100 kilohertz with the right equipment. The top records, I think, are around 110 kilohertz. So, and I'm speaking of kilohertz, so you can do the math yourself. That's a very, very high frequency and spinning speed. So these things are tiny, but yeah, they are spinning fast. So why do we do that? Is that by spinning the sample, so both at that angle and also the high frequency, you can start to average some anisotropic interaction. So that include the CSA, the dipolar coupling, and some part of the quadrupolar interaction, but it can also average more than that. But yeah. And what I mean by averaging out is that if you take, for example, a carbon-13 spectra in static, so without magic angle spinning, you're going to end up with this very large signal. So here, that's glycine that we are looking at, and you should only have 2 signals. But if you take just the static spectrum, you can see this large signal, and you might wonder what is going to happen. Why? What is that? The reason is that you've got chemical shift anisotropy when you're dealing with solid, and that's what is responsible for this type of line shape. So then if you start to spin your sample, you're going to create, you're going to move from this to this. So this is just spinning at 1 kilohertz. So you can see that it is first much more intense in terms of signal. And if you're spinning not too fast or very slowly, the manifold of signal, which are called spinning sideband now, because we are spinning, is basically describing the line shape of the CSA powder pattern. But then if you go at speed that are large enough to average that interaction, you're going to end up here, which is pretty much only 2 signals that are very sharp. You have tiny spinning sideband still left here, but at that point, you've reached a resolution that is almost as good as what you would have in liquid stain sample. And that's the reason why we're doing magic angle spinning in solid, just to improve the resolution. If now I take another example, so it's still glycine, but now proton NMR, you see that from here to here, yeah, sorry, they are not in the same direction, but from here to here, I'm spinning faster and faster. When I'm in static or even at low speed, the resolution is not really better. I think we can all agree on that. But at some point, if you reach a high enough spinning speed, the resolution is going to start to improve. And the reason is that magic angle spinning is also averaging the homonuclear dipolar coupling, which in the case of proton, if you remember what I was telling you about the dipolar coupling, is a very big problem, because that's going to significantly broaden the spectrum. But if you spin fast enough, you can start to average part, at least, of that interaction and get back to a pretty well result, or well enough result for solid state spectroscopists, at least, to get the information that you are looking at. And yeah, that's why that's all I wanted to tell you about the magic angle spinning. But yeah, this is important. So now I'm going to move on to the actual reason why you are here, the NMR of batteries. Before doing that, maybe I should ask, do you have any question, or if something isn't clear? No?
I was going to say, maybe we can go to some of the applications soon, because it's 9:58.
Oh, sorry. Okay, yeah, I'm going to talk about the application, and that should be fairly fast. Yeah, sorry, I don't have a timer or anything. Yeah, so now I talked about the theory. It's done. You can start to breathe again. So why am I talking about NMR of batteries? So I'm not gonna explain how battery works, but just quick information here. I'm going to focus mainly on lithium-ion batteries, but most of the things that I'm going to say are also applicable to sodium-ion batteries. So NMR, in fact, can study many parts of a battery. You can do cathode, anode, electrolyte, even cell. You could, in fact, do imaging, like I'm going to talk about cell, but yeah, so NMR almost useful for anything you might want to. But the first thing is that you have to think, are you dealing with lithium ion or sodium ion based system? Because in terms of NMR, the approach is going to be slightly different. If you have a sodium ion based system, well, the choice has been made for you. You have only one nuclear isotope that is NMR active for sodium. So yeah, no problem. The path is straightforward. But if you have a lithium system, now you have two isotopes, 6 lithium, 7 lithium, which have very different NMR properties. And in fact, if you look at spectrum on the same system, so this is lithium manganese oxide, on top of that, you would have the 6 lithium spectrum and 7 lithium on the bottom. If you look at the NMR parameters, just because of the high natural abundance and high ferromagnetic ratio, 7 lithium is pretty straightforward to record and give you this type of spectrum. But if you look at the 6 lithium spectrum, you have a spectrum that is much less crowded, so it's often much more resolved. But the problem is that 6 lithium is only 7.6 abundant and has a low gamma value. So it's still feasible, but it's going to take more time and often going to require isotopic enrichment or labeling if you want to do 6 lithium NMR. But both exist and they have like pros and cons. So after that, I was talking only about the obvious nuclei and which one to choose, but you have many more than just lithium and sodium in a battery. And for example, if you're dealing with electrolyte, oxyfluorides, fluorides, or phosphate system, well, proton, carbon, fluorine, and phosphorus are all spin 1/2 and have very good NMR properties. So yeah, they also can provide a lot of information. If you want to go on a more exotic side, if you're dealing with vanadate or if your structure is aluminum doped, both aluminum and vanadium have also pretty good NMR properties. Keep in mind that they are both quadrupolar because the spin number is higher than 1/2, but still quite useful. And the bottom line is that you have a very large amount of systems that are possible, and you should just think a bit about what the NMR nuclei in your system might be and which type of information you are looking at. So don't just rush lithium and sodium NMR, just thinking ahead and plan your experiment. So now, what can we learn with NMR of batteries? So this is a list of all of the things you could do with NMR, and this is non-exhaustive. So I'm gonna try to walk you through this, and I'm gonna start with the local structural characterization of batteries. So here, the thing is that when you're recording, for example, a lithium spectrum, the thing that you want to, or the first thing that's gonna show up is the isotopic chemical shift from the chemical shift interaction. This value is expressed in ppm, and that value will depend on the actual local environment of the lithium or the nuclei that you are working with, which means that by knowing the chemical shift, you can reach the coordination state, or you can identify the phase that you have, or even show some phase transformation depending on what your system is doing. So here I'm putting an example from the literature where you have different manganese-based compound, and if you're doing lithium on this, for example, on manganese spinel, you're going to have different values that have been reported for the lithium. One thing to keep in mind is that when you have a diamagnetic system and you have lithium in it, the chemical shift of lithium is going to be around 0 ppm. But here, from these reported values or range, you can figure out that if you are not in a diamagnetic system, like all of these are, spinel is containing manganese ion, which are known to be paramagnetic, like any or most of the cathode materials. The actual lithium environment, if they are tetrahedral or octahedral, can reach up to 2000 ppm. So there is a huge shift, and that shift is provoked by the paramagnetic interaction that I was referring to. So now, if I take an actual spectrum, and this is in fact a spectrum that I obtained on one of Howie's composition, so thanks Howie for that. This is here, lithium-rich lithium manganese nickel oxide. You can at least see 4 environments here, 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 and here. And from published literature, I can have an assignment done. And if you look at the assignment, you see that the lithium is in fact surrounded by different amount of manganese and nickel in different combination. And this different change in the local environment is affecting the chemical shift. And that's why I can distinguish all of these different signals. On top of that, since it's a layered structure, you have both lithium layered, or you should have lithium layered, but it's also a lithium rich system that some of the lithium is going into the transition metal layer, and that's going to affect also the lithium environment. So you have that separation of the signal and you have multiple sites. If now I move on to a more advanced spectrum that I don't know if you've checked, but see that, but here that was spinning sideband, so I can erase or remove them with the clever experiment. Now I'm only having my 4 signal and I can fit them and obtain the actual integration of the signal that relates to the relative amount of lithium in each environment, which is quite useful. For example, doing that with XRD would be very difficult or even impossible. So now I'm moving on to a different topics. Imaging, like I told you in the introduction, you can also do imaging with other nuclei than proton. So here, this is 7 lithium chemical shift imaging, and that slide is coming from Olivia Wonder in my group, who is working with this type of system. And what you have to remember is that it's a different approach from MRI, but it's still the same principle where you are creating an image. And in fact, here, what they were doing in that study is that they were following the lithium dendrite growth in a cell made of LLZTO solid electrolyte. So at the beginning, you see these 2 signals, which are the lithium electrode on both sides. So this is a symmetric cell on both sides of the electrolyte, and then they start cyclate, keep on recording multiples, not spectral, but image. And here you can see that this new signal appears, and they are in fact the reason why they were saying that lithium dendrite were growing, because this is the chemical shift of lithium dendrite, or typical from lithium in a dendritic environment. So continuing with a more imaging technique. So in that study, they were proposing to use MRI. So no longer dealing with 7 lithium, but going back to proton to be used as a non-destructive quality control of lithium ion cell. And here, in fact, this is an indirect method for MRI for an MRI system. They are not actually looking directly at the battery, but they are looking at the impact of the battery around itself, and especially the change in the magnetic field that it induces in that sample holder. And they were imaging the sample holder and see how defects in the cell, like manufacturing defects, could be seen. And so the good point is that this is actually working on the on commercially available cell. You don't need special cell, and it's also a non-destructive technique. So from a quality control quality point of view, that's could be a game changer. So now I'm moving away again from imaging, but going now to liquid state NMR, because this is also quite useful. And if you look at that study, they were using liquid state NMR, so proton, carbon, fluorine, and phosphorus, to study the degradation mechanism of a typical 1 molar LiPF6 in EC-DMC electrolyte solution that they were cycling using a lithium cobalt oxide cathode. Here, this is a very interesting approach because they were using a custom swage lock cell that avoid them to have the electrolyte from the cathode and the anode side being mixed upon cycling. So they were able to extract both sides of the electrolyte, record their NMR spectra, and then as the assignment, they were basically showing which type of new molecules were formed upon electrolyte decomposition. So to do that, they were doing some 2D NMR experiment to get the full assignment. And I have to say that this type of works is really major because this is really time consuming. This is not the small study, but yeah, this is really important because if you have now the degradation product and you observe them on both the anode and the cathode, you can start to propose a mechanism for the degradation pathways. So now I'm again switching gear. Sorry, this is very fast, but I'm trying to save time. I'm moving to another type of NMR that I haven't talked about yet. This is called PFG NMR for pulse field gradient. And here that's used to study solid state electrolyte and also polymer gel. But the thing you have to know with PFG NMR is that it relies on the spatial encoding and decoding of the NMR signal within your sample, which allow you to track the motion of molecules, and that tracking is done by tracking the actual NMR signal of that molecule as a function of time in your sample. So like I said, this technique can be employed when you're studying potential solid state electrolyte like this lithium yttrium chloride. And in this type of materials, you have to know that depending on the synthesis condition, either by Paul milling or solid state synthesis, you can generate defects in the structure that are going to impact the lithium conduction. And if you perform PFG NMR experiment, you can extract the diffusion coefficient of the lithium in the structure. And if you do that at multiple temperature, you can then relate the diffusion coefficient to the actual activation energy barrier of the lithium migration. And this is what is shown here. So still working with PFG NMR, here I'm now focusing on the polymeric ionic liquid, which is here having lithium ion and TFSI ion as a charge carrier. And again, in such system, if you run PFG NMR, you can monitor the diffusion of both lithium and TFSI ion separately. But knowing these two diffusion coefficient, then you can move back to the lithium ion transference number, which is not something that is easy to get, for example, from impedance spectroscopy. But from the PFG NMR, you can get that. And this is really useful because in this type of system, you want to maximize the charge carrier capacity of your lithium because that's the one you care about. And by doing that, you can, in the end, just improve the structure of the polymer that you are working with just to favor that transference number for lithium to get the best performance out of your system. So with PFG NMR, I was talking about electrolyte system, and I just showed you that you were tracking large molecular motion in your sample. But in fact, NMR is also able to track a multiple range of dynamics processes in your sample. And depending on the time scale of that processes, you would have to choose between different type of experiment. Here, this is what PFG NMR was looking at, but you see that with this type of experiment and parameters, I'm not going into details, but you can have a much wider range of dynamic processes. So this is another study where they were doing some chemical exchange experiments. So we are in that range now of time scale. And here the thing is that they were mixing two phases to create an electrolyte, solid electrolyte blend. And I'm not going to describe everything, but the bottom line is that they were able to extract from this data set the actual fastest chemical exchange between the two phases for the lithium, and they figure out that this mixture and that of that sample was giving you the best performance. So yeah, I'm going to end here with the final example because I found it quite interesting. And this is in situ monitoring of redox processes by solid state NMR, 7-lithium in that case. So this has been done multiple times now. And this is quite interesting because this type of system allows you to record an NMR spectrum while you are actively cycling a cell within an NMR magnet. So from just that sentence alone, I am pretty sure you understand that this is not straightforward and that's requiring a lot of careful planning and some special hardware. But nevertheless, you can agree, I think, that it's has a lot of benefits since you are being able to investigate all of the components at once on the same batteries at different state of charge, and you don't have any risk of contamination or you don't have to make multiple cells. So that's always a bonus. In particular, if you look at that study, so it's actually not a lithium-ion cell by itself, but it's made of carbon. So in that study, they were proving the lithium insertion and deinsertion in carbon. And you see that with the lithium signal moving from between the LiPF6 original electrolyte to the typical lithium signal chemical shift that you would have for inserted lithium in graphite. And with that, this is just a summary of what I was talking, and I'm reaching the end of my presentation. Sorry for being so long. I hope I managed to show you that NMR is a powerful technique and it can provide valuable information when you're working with NMR batteries. This can be applied to a large variety of systems and can give you different information, and you have a large variety of methods to get there. And one thing to know is that these methods are always improving. And because of that, I would highly encourage you to reach out to NMR spectroscopists if you want to obtain a particular information for your system, as they might have some new experiment they could give you that would be the best suited candidate for your type of application. And in fact, this is more general, but you can do that with any kind of techniques. It's always a good idea to talk to people that have more knowledge about a particular type of technique. And with that, yeah, I just want to thank my group, the NMR facility, because yeah, I'm bothering them quite a lot. Also the DOE for the funding, and of course you for your attention. And if you have any question, please feel free.
Thank you, Raynald.
Yeah, sorry for being so long.
No worries. We still have people here, so.
Okay, everyone is still alive.
Everybody is still alive. All right, any questions from the audience? Okay, I have one. If I am doing battery research and I want to learn about the structure of my material, my go-to is X-ray diffraction. And I can do X-ray diffraction and learn about the structure. Why then would I go towards NMR to learn about my structure?
Okay, so yeah, that's something I haven't talked about, but that's very good question. The thing is that XRD is only local seeing the crystalline structure, so the long range order in your materials. So first, if you have a non-crystalline solid, well, XRD is not going to help you at all. But NMR, on the other side, is looking not at the long-range order, but the local environment of your nuclei. So it doesn't rely on any kind of ordering, and you would see, in fact, the difference between ordered and disordered phase. So in that case, or even if you have a crystalline structure, if you want some information on the local environment that are not visible in that case in XRD, NMR is a pretty good idea. The thing you have to remember is that NMR is a local probe, really, not a long-range one. Yeah, I hope that answers your question.
Anybody else have questions?
They are just too tired, or they left.
Okay. All right. Well, we'll call it there. Thank you so much, Raynald, again for presenting. I'm gonna
yeah, no problem.
in here.